Hello and welcome to Make Learn 360. In this video, I want to solve some couple of problems with you to illustrate the concept of um, internal forces in axially loaded members. Let's look at the problem together. So we have a steel over here, a steel bar with a rectangular cross section. It's used to transmit 4 axial load as shown. Now we are to determine the axial forces transmitted by the transverse cross sections in intervals AB, BC, and CD of the bar. And then also we should draw an axial force diagram for the bar. Okay. All right. So how can I solve this problem? Now, don't forget that there is a P here, which we don't know. So let's start by solving for P. So we are going to say that summation of forces along the X positive in this direction should be 0. Okay. Um, so that is it. Um, we are going to start. So minus 35 plus P minus 20 plus 18 is 0. So we are just looking at the sign of the forces. Solving for this, what can we say P is? All right. So we can say that, so P is going to be 35 plus 20 minus 18. What is that? So it's going to be 35 plus 20 minus 18. 37. Oh, so P is 37 kip. All right. That is kilopound force. Okay. Now we know P, then we can find the internal forces. So let's start from looking at the force in member AB. So this is member AB, okay, or section AB, okay. So this is section AB. If I want to look at the force in section AB, what I will do is that I'll cut section AB. If I cut section AB, I'm going to get something like this. So it's going to be something like this. And this is where the cut is. Now, over here at A, the force is what? 35 kip. So to make this body be in equilibrium, we need to attach a force which is what? Equal but opposite, so that it becomes it is in equilibrium, so that it will be 0. Interestingly, what this means is that that force must be FAB, which is equal to what? 35 kip. That's all. So this body is in equilibrium. I hope the concept is clear. This body is in equilibrium. Therefore, the FAB which we want, or the force in cross section AB, is 35 kip. All right. Now, again, to get the force in section BC, we will come and stand here and cut between B and C. Okay. So when we cut between B and C, what are we going to see? So we're going to come here like this, all the way here, all the way here. Now, this is where we introduce the cut between B and C. So this must be something like B. The force at B is the one that we know here as P. So what is it? P is what? 37. It means that this force is 37 kip. All right. And don't forget that there is a force here at A, which is what? 35 kip. Okay. So if here is 37 kip and here is 35 and here is 37, we need to add a force to this to make this be in equilibrium. And that force is the internal force in BC. And so simply put, to know the magnitude of the force to add, let's look at whatever we have here. Okay. Let's look at whatever we have here. Okay. Now we have 37. Sorry. So minus 35. If I say minus, so this is what I'm trying to do. Summation of forces, every force positive in this direction. Let's look at that. So it's 35. So 35 is minus 35 plus 37. It will give you what? 37. Or okay, let me do it this way. Minus 35 plus 37. That is what? 2, isn't it? So 2 kip. Now, what this means is that the external force on this is 2 kip. For this body to be in equilibrium, then we need to add a force which is opposite to 2 kip. Therefore, to make everything 0, so this is what we are saying. To set this portion to equilibrium so that the summation of the forces will be zero, we need to attach a force here. If we do that, we need to attach a force in this direction, which is what? 2 kip. As a matter of fact, that force is FBC, which is what? 2 kip. Now let's try and see if we add all of them and get zero. So minus 35 plus 37 minus 2, 0. It means that FBC over here is actually a compressive force. Okay. So in other words, FBC is minus 2 kip. So we've been able to solve for FBC. But don't forget that for the FAB, the force was here. So the force needed to set equilibrium was in this direction. So this one is actually like a tensile force. So it's positive. Okay, so this is a tensile force. And then this is what? A compressive force. All right. I hope the concept is clear. Finally, let's cut between C and D to find the force in CD. Let's cut between C and D. If we cut between C and D, what happens is that, so it means I'm going to reproduce the whole thing again. Okay, let's do that. So if I cut between C and D, I'm going to get the whole of this again. So all the way to where the cut is. All right. But we have to indicate the forces at point A. So this one is what? 35 kip. And then what do we have again? At point B, we have P, but we know P, isn't it? We know P as what? So this is at point A. Now this is at point B. What do we know? We know the force at point B is what? P, which is 37. So 37 kip. And then what else? At point C, we have 20 kip. So there is 20 kip in the direction. All right. So that is it. So the cut is between C and D. Okay. So we are looking at this cut, but we have to indicate all the forces all in this direction. And that is what we have done now. Okay. Now, for this member to be in equilibrium, we need to find the external force or the summation of the forces. Then we will know which force will cause it to be in equilibrium. So summation of forces again is going to be what? So minus 35 plus 37 minus 20. Okay. So what is that? Minus 35 plus 37 minus 20. If I do this, I'm going to get minus 18. So what this means is that the external effect of all the forces here is minus 18. Therefore, for this body to be in equilibrium, I need to get a tensile force. So minus 18 means it's actually a compressive force. So to make this whole thing be in equilibrium so that the summation of forces on it will be zero, then I need to attach a force of equal magnitude, but in the direction which is tensile. And that force must be FCD, okay? Which is what? 18 kip. But it's supposed to be tensile force so that it will cause the body to be in what? Equilibrium. Now let's attempt to sum the forces this time and see what will happen. So I have 35, okay. So minus 35 plus 37 and then minus 20 plus 18. Boom. So we had 0. The 0 is telling us that we needed FCD to be 18 kilopounds. And then it's a tensile force. Okay. So please note the difference. If you solve for the force in the member and get negative, it's a compressive force. And if you solve for the force in the member, you get positive. That means it's a tensile force. So we've been able to solve for the force in member AB. That we got what? So the force in member AB, we got 35 kip, right? And then it was a tensile force. And then the force in member BC was what? 2 kip, but it was a compressive force, so minus 2 kip. Finally, the force in member CD is what? 18 kip, which is a tensile force. Okay, um, we are done with the first part. The second part, he said we should draw an axial force diagram for the bar. So an axial force diagram is nothing but so we are just saying that okay, we are having a diagram which illustrates the portion which is in compression and which is in tension. So this is how we are going to do the diagram at the various points. Okay. So through now the member, what is happening? All right. So what this means is that let's say this is 0. Let's go to the diagram. From A to B, what did we experience? We experienced a tensile force of 35 kip. It means that I'll move from 0 and then I'll move to 35 kip. Okay, so let's say that this is 35. Okay, then I move to 35 kip. That's what it means. Then there was a constant force through out AB, but as soon as I went to section BC, there was a force of what? Minus 2 kip, which is a compressive force. So this portion is for the portion AB. Okay. Then finally I came to minus 2. So minus 2 means you come below, right? You come below this one. And then you have this one here. You know, this is positive, but this is negative. And then it's what? So it's actually minus 2 kip. Okay, we don't need to indicate it. The unit is actually in kip. And then finally, what do we have? When we go to FCD, we had 18. It means I have something like this, which is not, let's say, half of the 35. So maybe something like this. Okay, and this is what? Positive. So from here to here is member AB. From here to here is BC. And then from here to here is what? CD. So we call this diagram the axial force diagram. Okay. So this is what we call the axial force. So the axial force diagram. All right. Okay. So this problem has been solved. Okay. Let's look at the last problem in this problem set. All right. All right. So let's look at this problem. Um, that is going to be the end of the tutorial. Now let's look at this problem. So over here, you can see that there is a support reaction over here. Therefore, we need to find the reaction from the wall to um, the member, okay, or the bar, okay. So to do that, we are going to draw the same thing over here, and then we are going to look at the force or the reaction force. So basically, I have something like this over here. All right, so I have this from okay, so this is the wall. There is a force of 40 kip in this direction, and then there is a force of 40 kip again. Now I have a force at this point, which is no, it's actually here, 50 kip. Okay, and then finally I have what, 10 kip. All right, so these are the forces acting on the member. Now for this member to be in equilibrium, we need to find the reaction force. Okay, so what is the reaction force? What is the magnitude of the reaction force acting on this body? That is what we want to know from the wall. That is the first thing to do. Okay, so for this member to be in equilibrium, summation of forces to be 0. Okay. So it's going to be what? R minus 40 minus 40 plus 50 plus 10 to be what? 0. So R is going to be 40 plus 40 minus 50 minus 10. And what is that? So 40 plus 40 minus 50 minus 10. So R is 20. Okay. Now what this means is that if R is 20, then we can go back and just put 20 over here. Okay. And that is actually the reaction force from the wall to the bar. Now let's indicate the section of the bar. Here is A, here is B, this portion is C, and then this portion is D. All right. Okay. So after doing this, let's find the internal forces A, B, B, C, and C, D, and then we draw the axial force diagram. So to find the internal force in AB, we will just stand here and cut portion AB and then draw what we have. If we do that, then it means that for the portion AB, okay, so basically it's like saying that standing here and cutting through this portion. If I do that, then it means that I have this 20 coming from the wall as a reaction. Then I am just cutting like this. Okay. Now this is point A. Watch this carefully. For this portion which I have cut to be in equilibrium, then I expect that the summation of forces must be 0. And what condition will this be 0? When I have an equal but opposite force. So let's call this FAB, and it's what? 20 kip. In other words, what we are trying to say is that the force acting on this is 20 kip. So to maintain equilibrium of this, then it is expected that FAB must be what? 20 kip in the opposite direction. As a matter of fact, FAB is a negative force because we said that every force going here will be positive, right? And then this force is what? Coming the opposite. So FAB is minus 20. In other words, think about FAB as a compressive force. So 20 kip, and then you say compressive. Okay. So FAB is a compressive force. All right. Let's look at the other forces. Now to get FBC, so we are done with FAB. To get FBC, you come here, cut through BC. Okay. Now if you cut through BC, then you are going to produce whatever you have up to BC. Okay. So it's like cutting here. Okay. So let's say we have cut this portion and we want to draw it. Okay. So let's draw that portion. All right. So when I cut between BC, so this is what I've done. I've cut between BC. All right. And this is what I will get. Now we need to look at the forces acting on the whole of this portion. Let's look at the forces. So summation of forces along the x, every force in this direction is positive. Now let's do this. So 20 minus 40 minus 40. So we have what? Minus 60. Now, if we have minus 60, then what this means is that the summation of all these forces is minus 60 kip. Now, to make sure that the whole of this portion is in equilibrium, so minus 60 is like a compressive force. It means we need to attach a force which is the same magnitude as 60, but it's a tensile force. So let's say the force must be here. In fact, this force is the FBC, and this force must be 60 kip. All right. This force must be 60 kip. So FBC is 60 kip, and then it's what? A tensile force. All right. Now, interestingly, look at this. Let's try to sum the forces. Again, let's try to sum the forces. So 20 minus 40 minus 40 plus 60. Or what is it? 0. So it means that this portion is in equilibrium if I have FBC in the tensile force direction. So this is tensile, this is compressive. Finally, let's look at CD. Now, to get the force in member CD, again, we are going to take the portion or the cut between C and D, okay? Between C and D. So let's take the portion this time around. Let's do it between C and D. Okay, let's do it between C and D. Can we do that? All right. So if I cut between portion C and D, I am going to have something like this. Now, what this means is that, okay, again, let's look at the forces acting on the whole of this. So now we are looking at the whole of this, okay, the whole of this. Now, if you look at the whole of this, what is the forces? We are going to sum forces along the x. Okay, what are we going to get quickly? So 20 minus 40 minus 40 plus 50. What is it? Minus 10. Wow. It means that the summation of all of the forces acting on this portion is 10 kip in the negative direction. Now, what this means is that for this whole portion to be in equilibrium, then I need to attach, so minus 10 means a compressive force, right? So I need to attach a tensile force of magnitude, but then, of course, that is the FCD of 10 kip, all right? So in other words, we are saying our FCD is a 10 kip tensile force, all right? So a 10 kip tensile force. Now, interestingly, what this means is that let's try and sum the forces this time and see. So 20 minus 40 minus 40 plus 50 and plus what? 10. Boom. So we had 0. Why did we get 0? It means that the force which is required to make this portion be in equilibrium is the FCD, which we have gotten as 10 kip. All right, I hope the concept is clear. We've been able to solve for FAB, compressive, FBC, tensile, FCD, tensile. Okay. All right, so now we have the forces in the members. Um, let's look at the, let's look at the axial force diagram. Okay, let's look at the axial force diagram. So now the axial force diagram is nothing but um, a diagram which represents the axial forces. So as I move through the cross sections, so let's say that this portion is my origin, which is 0. From A, so from A to B, I have a compressive force of what? Minus 20. Okay. So then it means that from 0, I came down, so I go to minus 20. I maintain this throughout, so I go to B. So what this means is that the whole of this portion represent the axial force in member AB. Okay, so member AB, and it is actually negative, which is what? 20, right? Kip. So the unit is in kip, right? So we don't need to bring it. So the negative sign means it is compressive. Again, from B to C, we came to 60. So from B to C, it was 60. So 60 need to be bigger than that, right? Anyway, it's not drawn to scale. All right, so that is our force, axial force. Now over here, this is 60, right? Okay. So I'm trying to say that this is 60, isn't it? So the magnitude is 60. Finally, FCD was what? 10. Okay, so something like this. Let's say this is 60, then it reduced to what? 10. So we are saying that over here we have what? So we have 10. Okay. So this portion from here all the way to here is actually BC. And then from here to here is what? CD. Now, when you're able to do something like this, we call it the axial force. So the axial force diagram. Okay, some people would like to add, so sometimes some people would like to add 20 and then they'll add C, which is compression, and then they'll add 10 and they'll add T here, which is tension, and then 60 and then T here. Well, for me, it doesn't really make sense because it is positive. That is why it's a tensile force. So I don't really need to worry myself bringing it. All right. So the problem has been solved. Thank you very much for watching the video. Kindly like the video, subscribe to our channel, and share it to your friends offering engineering. Strength of materials. This is actually strength of materials, and there is more to come. Thank you very much for watching once again.